Okay, right. Thank you, everybody. We begin with an online talk. It's from Daniel Hampf, and it's going to be on the miniSLR, a low-cost, high-performance laser ranging system for the ILRS. So, hello, Daniel. Okay, so Daniel, if you can hear me, please proceed, share your slides, and off you go. Thank you.
Okay, can you see my slides and hear me?
We're not hearing you, Daniel. Can you hear us?
Yeah, I can hear you fine.
Hello. Okay.
Yeah? You hear me now?
Yeah, it's good.
Okay, it didn't change anything. Okay, good. So yeah, thanks, Matt, and thank you all for the opportunity to give this presentation here, and especially that you went the extra mile to make it possible to do it online even. Since I can't be there with you for the coffee breaks now, let me take a minute to say a few personal words. I thought that reconnecting the community is such a great motto for this workshop, because really it has been 3 years since we've seen each other in person. Really since the Stuttgart workshop 3 years ago, which I remember quite vividly, of course, for obvious reasons. But also, in fact, because just a few days after that workshop, our first child was born. And if you look at her now, you can see how long actually we didn't see each other. So it's sad that I can't be there with you, but as a funny coincidence, actually we're expecting our second child just in a few days from now. So yeah, I don't know, correlation is not causality, but it's a bit funny. So that's why I'm currently grounded in Stuttgart and can't be in Guadalajara with you. But yeah, anyway, I'm following online. It's really interesting. Thank you. And I also want to mention that I have a bit of a new professional situation. I continue to work at the German Aerospace Center, which I've done for almost 10 years now, but I'm also 50% at DGOS Potsdam now with André Claude and Jens Steinborn, as you know, and we're doing interesting stuff there as well. Right, so the miniSLR, why would we want to do something like a minimal SLR? Well, as you know, SLR is still a complex and expensive thing, and it still features a sparse global coverage, even though all of these points are improving over time. But definitely we also have a constantly rising demand. We have more high precision Earth observation missions that need support. We have better theories and models that need good global coverage to be tested. We have more GNSS constellations like Galileo, but also the regional ones in Asia that need support. But we also have new applications like space traffic monitoring, as Tim mentioned this morning in his talk, that are visible on the horizon and could potentially lead to a huge increase in demand for SLR ground stations. So our idea is really to, by developing a simplified and less expensive and more flexible SLR system, we can hopefully, facilitate these new applications, but also enable new players to join the game. And for me, as a native Brazilian, I especially would love to see more institutions from the global south joining the ILRS with their own systems, and from South America, from Africa, and maybe the miniSLR can be one step along the path to that happening. And also it could help, to relieve high-end stations. We have these fantastic stations that can do about everything from space debris to deep space ranging, time transfer, lunar laser ranging, but spend their days tracking Galileo and Archizai and so on. So that could also be an idea, to just have a miniSLR next to a high-end station. So how does it work? Well, the basic idea is to reduce complexity, and mainly by concentrating on one thing, just saying, okay, we just want to do SLR, we don't want to do anything else. Like in this Linux philosophy, you have one tool to do one thing, but do it well. And a few things to reduce complexity. First, we start with a small telescope. We have a 20-centimeter telescope here. You see the specs in the table here. A small telescope means you can have a small mount. A small mount means you can have the whole thing not on a concrete pillar in a big building, but it can be on an aluminium or steel box The box you see here weighs about, the whole thing weighs about 600 kilograms. It has wheels on the bottom. It can be pushed around by 2 people. It can be lifted by a forklift. It can be put in a van for transportation. And of course, once you're happy with its position, you put up the wheels and put it on solid feet. That's how it operates here. Of course, it's not standing on wheels then. But you don't need a dome. The whole thing is fully encapsulated. The idea here is also to have an inherently safe system and situation. So we don't have a UPS on these things. So if it fails and you're operating that remotely from home, which we do occasionally, and you lose connection and everything, it just doesn't matter. You just leave it there. It's rainproof, and you can just cycle up there next day and see what you can do about the situation. So you don't need anybody on site who can rush there and close the dome in case it's stuck or the rain coming on and so on. You don't need a building. You don't need a building permit. You can just put this on a parking lot or on the top of your building or wherever. If you look at the specifications down there, what you see there, we have a rather strong laser with 5 watts. We need that, of course, to offset the small aperture of the receiver and overcompensating a little, actually. We do this by going to a rather high average power but low pulse energy. So we go for 50 kilohertz but 100 microjoules. We do this simply because it is sufficient, and on the other hand, it makes the laser much simpler. So the laser we have in there is just the size of your palm of your hand, which you would never achieve with a mode-locked picosecond laser with 5 watts, of course. And we have the laser just in the top compartment there. I'll show a picture later. Then about pulse duration, well, the system you see there on the right in the picture has been operating on our roof of our institute since the beginning of this year. And it has used a 5 nanosecond laser just because we had it available. We had ordered a picosecond laser a long time before, but it didn't arrive. Then we ordered another one, which has finally arrived a few weeks ago. And we have just integrated it now a couple of days ago. So that now will be 500 picoseconds from now on. So you may ask, okay, 500 picoseconds still isn't like 5 or 10 picoseconds like the other systems have. So how you want to achieve millimeter accuracy? And the answer, of course, is by statistical averaging. So the idea is your systematics, of course, have to be accurate to the millimeter level, but then you can allow for a certain statistical variation in your distribution. And that's all you get really from a long pulse. And then by averaging over a few thousand pulses, you will get to below 10 picoseconds or so on average. So you see a few ranging plots here we have recorded over the month. On the left is a 15-minute pass by Lagos. We see that we have a few thousand data points per normal point, which should be enough to bring us down by a factor of 50 in statistics. You see we have a return quote of much less than 1%. Even with the low-flying objects like HSI or so, we never go above 5% or so, which means that we don't need return rate control, and we're always inherently adhering to the single photon level, so avoiding all statistical complications there. We can also track Galileo. It's a bit on the edge of what we could do with our previous setup, but this is from April, and I think we're a bit better these days. So yeah, hopefully we can also get good tracks from the navigation satellites there, even if it's with less data points per normal point. Yeah, we also looked at some space debris with retros like Diadem here, or the Chinese rocket bodies, just because we like ranging space debris. We have done a few rounds of analysis by Toshi, and I really like to thank you, Toshi, for your continued support, both in practice with your work, but also morally throughout this whole project. We see that we still have a large pass-to-pass jitter of a couple of centimeters, but this has all been data from August with our nanosecond laser, and we do think that this should improve drastically with our 500 picosecond laser now. We'll see how the numbers really look then. It's a bit too early to say, but of course the goal is to come to drastically below 1 centimeter in accuracy and to compete with the current systems that we have worldwide. So we should really say, because people always say, okay, this is a cute little system, but we should really say we don't go through this whole effort to have a toy. Yeah, this is really meant to be a high performance SLR station that can meet today's standards that you would have. So where are we going? First, maybe I draw your attention to the slide, to the picture on the top right. This is I sneaked in this just yesterday. This is the first pass we recorded with our new sub-nanosecond laser. So we're quite happy that it's working now, and we're really excited to see where this is leading us. But this is really the first and last pass we recorded with that. So far, the only one on Monday, but there will be more following soon. We, yeah, and also in the bottom picture there, in the photograph, you see our laser. It's this little silver box in the middle with the yellow warning sticker. It's really just 10 by 10 centimeter. Yeah, we plan to submit data to the ILRS, not so much to improve the data products. I mean, we're in the middle of the most productive stations in the network between Hörsmann-Su and Graz and Zimmerwald and Graz and Potsdam, Wetzel. So probably we can't help much there, but we have, the idea is more that we get a neutral feedback on our accuracy, because everyone's saying, okay, this is a nice system, but can you really meet the demands that what we want to have with millimeter stability and accuracy and so on? And I think the best way to prove that is from an independent analysis done by the analysis centers with the same kind of standards that you would apply to all the other stations. So hopefully in the near future, people can just go to the monthly report cards and see the Stuttgart miniSLR there and make up their own minds about the performance. I also want to mention that we cooperate with DGOS, and maybe you remember the first slide about my personal situation. So at the DGOS, we have the plan to commercialize this miniSLR system. So the idea is that if you now sit there and think, wow, well, this is really cool, and I want to have one of these miniSLRs, there's basically two routes to that. Of course, you can build one yourself, and we could even help a little bit with that. We could talk about this. But if you say, I don't want to go through all the effort, I want a pre-installed system with a user manual and warranty and yeah, just coming to my place assembled, then yeah, DGOS would be the place to go and ask about this. And I think we can give you a very good offer of how to do this, and should have also a short lead time of maybe a year or so from placing the order to having a system on your site that works and does SLR. And we actually already sold the first platform. It will not be equipped with a laser ranging system because the customer didn't want it, but it will be the base system for tracking and the electronics and so on. And that should be delivered by next summer or so. Will be looking a bit different from the DLR miniSLR, but yeah, inspired by that. Yeah, and I'll leave you with that, with a nightscape from Stuttgart. Yeah, I would like to thank the whole team that made this work possible, and also the people from the ILRS for the continued support. And yeah, thank you all for listening. Thanks. Thanks.
Thank you, Daniel. Would anyone in the room like to ask a question? Okay, no questions, Daniel. Let me just send you our best wishes for the next few days and weeks and months. So good luck with everything. Good to see you.
Thank
you.
Thank you, Matt.
Bye-bye.
Okay, all the best. Ciao.